The last function we're going to look at in section 2.2 is called the greatest integer function. You probably have seen it before. It's also called the floor function. And the symbols used are either this, my preference, or our textbook uses that. This means the floor or the floor of x, or the greatest integer less than or equal to x. Here's the definition of it. For all real numbers x, the floor of x is the greatest integer less than or equal to x. So obviously for any integer, it's just equal to that number. For any other number, for example, 5.2, the greatest integer less than or equal to that is 5. The floor of pi would be 3. So you basically cut off the decimal points, truncate them. But what happens when you get to negative 2.5? What's the floor of that? Say it.
Negative 3.
It has to go back to negative 3. So you can't simply say, get rid of the decimals, everything to the right of the decimal point. It works for positive numbers, but it does not work for negative numbers because you have to go to the next smaller integer.
So you always have to go basically left on the number line.
Exactly right. On the number line, you're always moving left, except for the case where it's an integer, where the greatest integer less than an integer is just that integer. It's the only one you wouldn't have to move to the left. Okay, well, what does the graph look like? Well, for anything from 0 to 1, the floor is 0. Up to and not including 1. From 1, including 1, up to, but not including 2, the height is a 1. And it just continues like this step. And even in the negative numbers. And so on. I'll just put dot, dot, dots. It goes on forever in both directions. This is the big step function. Well, the obvious thing is at every non-integer value, call it x naught, the function has a limit. I'll say the limit exists. Could have said f of x has a limit, right? Because if you're not an integer, if you're in between integers, you're basically looking at a constant function, right? So the limit of that function would be whatever the height of the function is there. Any question on why this is true? For example, this would be 3/2. The limit exists at 3/2 because if you the height of 3/2 is 1, f of 3/2 is 1, and if you approach 3/2 from either direction, all of those numbers that are close to 3/2 also have a height of 1. So the proof of that would be similar to just proving that the constant function has a limit. The only thing we need to worry about is, does the limit exist at integer points? At every non-integer value x naught, the limit exists. Maybe I'll take x naught away from there, and I'll say that at every integer point x naught, does the limit exist? Does not exist. And it's easy to see just by the graph. Pick an integer. Let's pick a nice easy one. Let's pick 0. Well, let's look at it as sequences. If you're a sequence on the x-axis, the positive numbers, and your limit is 0, you're going to 0 from the right. Well, f of all of those values in the sequence is just 0, and it converges to 0. But if you're just a little bit to the left of 0, if you're a sequence of negative numbers, f of each element in that sequence is -1. So it's a constant sequence of -1s, and it's going to converge to -1. So you found two sequences, or I just discussed two sequences that both converge to 0, but f of those sequences, one of them converges to 0, one of them converges to 1. So let's show this. Indeed, let's say that x0 is just our arbitrary integer. Consider the sequence that I'm going to define like this. x0 plus looks a little complicated. It is x0 plus -1 to the n plus 1 times 1 over n plus 1. So if we ignore the x0 part for a second, this is an alternating positive-negative sequence, right? Because as n goes up by 1, -1 to an even power is 1, -1 to an odd power is -1. So it's 1/2 negative. Let me start off with the right one. When n is a 1, that would be squared, so it's going to be a positive 1/2. So it's going to go positive 1/2, negative 1/3, positive 1/4, negative 1/5, positive 1/6, negative 1/7, and so on. It's a limit that it's a sequence whose limit is x0, because this sequence converges to 0. But, or since f, the sequence f of this, f of x0 plus -1 raised to the n plus 1 times 1 over n plus 1. Maybe I should have just put the -1 on top of the, actually that would have made it look a lot nicer. If I would have just put the -1 to the n plus 1 as the numerator of the fraction. So the sequence, when I take f of each one of them, is going to be equal to this sequence. Well, let me write it out. The first one is going to be f of x0 plus 1/2. Right? We already said that when n is 1, it's -1 to the 2, which is just 1. 1 over 1 plus 1 is plus 1/2. The second one is going to be f of x0 minus 1/3. And then f of x0 plus 1/4. I'll do one more. F of x0 minus 1/5. And that pattern continues. And we're dealing with the floor function, so my f of x is the floor of x. So that gives us the sequence, the floor of x0 plus 1/2, x0 minus 1/3, x0 plus 1/4, x0 minus 1/5, and so on. And since x0 is an integer, these numbers are easy to compute. What is the floor of x plus 1/2? x0. x0's an integer. So what's the floor of x0 plus 1/2? Just x0. What's the floor of x0 minus 1/3? Just put a number in there. Say if it's 10, what's the floor of 10 minus 1/3? It'd be a 9, right? So this is going to be x0 minus 1, correct? And then x0 again. And then x0 minus 1 again, and it repeats. So that's, which does not converge. I'm running out of room down here, so I'm just going to write which does not converge. And that tells us that at every integer point, the limit does not exist of this function. We found for every integer, we found a sequence that converges to that integer, but f of the sequence is divergent, doesn't converge. It oscillates back and forth, x naught, x minus 1, x naught minus 1, and so on.